Let's go ahead and talk about something else that's important for shell scripts, which is controlling process priorities. So the running instance of a program is process, and each process needs space in RAM and CPU time to be executed. Each process has its priority in which it is executed. The kernel stores a great deal of information about processing, including process priority, which is simply the scheduling priority attached to a process. Process with a higher priority will be executed before those with a lower priority, while processes with the same priority are scheduled one after another repeatedly. So guys, this is done through something called a nice value, okay? So nice values are a user space value that we can use to control the priority of a process. The values range from -20 to 19, where -20 is actually the highest, 0 is default, and 19 is the lowest value, okay? So we can check that out here. This may look familiar, this may look like top, but this is actually a little bit more interactive version called nmon, N-M-O-N, okay? But if we run top, we would see these same columns here. So we see this ni value, okay? And this is your niceness value. And I'll actually pull up my virtual machine here to show you guys here in a second. But we can alter this and change this to give certain things priority over the others. Here we have the top thing that we're normally used to, and we see we have a -12 here and -20. So this guy is actually going to get priority over all these other commands, and then -12, and then the rest would go one right after the other. Okay? And actually, this is good here. I don't need to show you my top command because here's the top command, the screenshot I took. Okay? Let's go and switch to our next subject here, which is interpreting command line arguments. So passing arguments to a script, arguments can be passed to the script when it is executed by writing them as a space-delimited list following the script file name. Inside the script, the $1 variable references the first argument in the command line, $2 the second argument, and so on. The variable $0 refers to the current script. So guys, in the following example, the script name is followed by 6 arguments. So we have /bin, so we have ./bin/myshopping.shell script, and we give it apple 5, banana 8, fruit basket, and 15. Okay? We're going to echo $3. So if we count here, 1, 2, 3. All right, 1, 2, 3. We get banana. If we do the variable big equals $5, and we echo a variable big costs just $6, that will result with a, and we count 5 here, okay? 1, 2, 3, 4, 5. A fruit basket, which is number 5, variable 5 here, costs just 15, okay? Because we said the variable 6 here, 15 is the last and 6th variable, okay? So the variable $hashtag or pound holds the number of arguments passed to the script. Okay, so it's telling you how many arguments are passed to the script. In this case, there are 6, right? Apple, 5, banana, 8, fruit basket, and 15. Okay, 6 arguments. And the variable $at holds a space-delimited string of all arguments passed to the script. Okay. So we can also make scripts interactive. So an interactive shell reads commands for users' input on a TTY or terminal. So TTY means terminal, guys. So among other things, such as shell reads startup files on activities, displays a prompt, and enables jobs controlled by default. The user can interact with the shell. A shell running a script is always a non-interactive shell. All the same, the script can still access its terminal. It is even possible to emulate an interactive shell in a script. So here we have our hash pling, and we have the variable my_prompt equals $, and then just a space, a blank space. So we say while nothing, do echo, and we echo the variable here, my prompt, and we say read line. So we're using the read command here, which is taking the user input and it's assigning it to the variable line, and we're going to evaluate the variable line, and done. We're going to exit. Okay? So let's actually look at special shell variables here. So Linux shell programming, there are special variables. The file name of the current script, and these variables correspond to arguments with which a script was invoked. Here is a positive decimal number corresponding to the position of an argument. The first argument is $1, the second argument is $2, and so on. So the command line arguments, variable 1, variable 2, variable 3, all the way to 9 are positional parameters, with 0 pointing to the actual command, program, shell script, or function, and 1, 2, 3, all the way to 9 are the arguments to the command. So we can say echo file name 0, which is pointing to the actual command. We say first parameter is $1, 2. We can say quoted values, and guys, if we go back one, remember this. We're going to go back 2 slides. It holds a space-delimited string of all arguments passed to the script. Okay, we'll go back to our original slide. We also have quoted values, and we have $*. Okay. And the total number of parameters. Remember, we go back 2 slides here. And that hashtag or # holds the number of arguments passed to the script. Okay. So these are all special shell variables here. Okay. Let's go ahead and move on to advanced I/O streams here. So a Linux shell, such as Bash, receives input and sends output as a sequence or stream of characters. Each character is independent of the one before it and the one after it. These characters are not organized into structured records or fixed-size blocks. Streams are accessed using file input-output techniques, whether or not the actual stream of characters comes from or goes to a file, a keyboard, or a window on a display, or some other I/O device. Linux shell uses 3 standard input-output streams, each of which is associated with a well-known file descriptor. We have standard out. This is the standard output stream, which displays output from commands, and it has the file descriptor of 1. We have standard error, which is the standard error stream, which displays error output from commands. It has the file descriptor 2. We have standard in, which is a standard input stream, which provides input to commands and has file descriptor 0. Guys, we talked about this in our last session as well, and we saw how to kind of move these and redirect these. Okay, this is important in scripts because it can be used to send things to other scripts or maybe files that are generated by scripts. Okay, so input streams provide input to programs, usually from terminal keystrokes, and output streams print text characters, usually to the terminal. The terminal was originally and guys, this word is pronounced ASCII or ASC2, ASCII or ASCII, sorry. So the terminal was originally an ASCII typewriter, a display terminal, but now it is more often a text window on a graphical desktop. Guys, we're going to finish out this session by talking about improving performance of scripts. So for better file handling, knowing or unknowingly, a lot of files are created or deleted in a shell script. Due to the use of a large number of files, handling of files becomes very important. Even a simple echo statement, which redirects output to a file, has to open the file first, write data into the file, and close the file. Use only the necessary commands inside a loop. It means not to use those commands which are not needed inside a loop, but it's common sense, right? The point here is, guys, just do not use commands inside a loop, which could be very well have been outside a loop, okay? Because we don't want extra memory being used or extra processing power being used if we don't have to, okay? We want these scripts to be as effective and as minimally resource intensive as possible. So whenever we have a requirement to write a script which is going to run on lots of files, the developer mindset is to write the script and make it work for one file. Once it works with one file, make it work for multiple files either by adding a loop or by passing command line arguments. Lots of performance issues happens due to this reason, okay? And avoid the useless use of any commands. There's a problem term known as UUC, which stands for useless use of cat. This means use cat command when it's actually not needed at all. So if we don't need to use a command, guys, don't use it, right? If the script or something else is going to do it anyways, there's no need to throw this command in there, right? You're just using up more power than we need to. So in summary, guys, we talked about manipulating strings, writing and calling functions, controlling process priorities, interpreting command line arguments, making scripts interactive, special shell variables, advanced I/O with streams, and improving performance of scripts. Next session, we'll talk about editing a file from a script, scripting with ed or sed, Unix and Linux utilities to manipulate files, regular expressions or regex, grep and egrep, the stream editor sed, sorting in scripts, generating reports with awk, splitting large files, counting words, lines, and characters, transforming file contents, and extracting text strings. Definitely be sure to follow these links, guys, if you want a little bit extra help. We do have private tutoring sessions available for system administrator management, weekly and monthly plans. We also have Linux and Bash scripting with private tutoring sessions. Thanks so much for joining me, guys. Hopefully you're starting to get a little bit of firm grasp on how this scripting works with Bash. And I'll be looking forward to seeing you in session 5.